Hello, and thank you for listening to this episode of the Night Sky Podcast. My name's Billy Newman.
And I'm Marina Hansen.
And we're here today to finally come back from our long hiatus. We've been on vacation.
Hey. Pretty good reason to be gone.
But we've been leaving everybody without an update on the night sky above us for now 2 weeks.
Oh, man.
Shoot.
Sorry, guys.
Everything's changed.
Sorry. One person who listens.
Last time we were talking about, oh yeah, there's been so many discoveries since the last time we were here. Gravitational waves have been verified. They've been projected before, but now they've been verified. I suppose. They say the math is strong. I'll let the scientific community vet that all. But yeah, they say that they found, what was it, like a 26 and I think it was a 26 and a 34 solar mass black hole orbiting each other. Came closer and closer, kind of spiraling in on their same like point. And then they finally merged together when the two giant black holes, a solar mass, like we talked about before, is the size of our sun. So one sun around Earth is one solar mass. So these black holes were each 30 solar masses, so 30 times more massive than the mass of the sun. And these two black holes spiraled in at each other. And it's at this rate, I think predicted in Einstein's theory of special relativity, where it kind of matches a pattern of how gravitational bodies will orbit around each other and then collide with each other. And so when these two bodies collided with each other, there was if you think of E equals mc squared as energy equals mass times the velocity of light squared, then what that would mean is that when mass is accelerated to a certain point, it turns into energy. That's what happened in this event. These two 30 solar mass black holes collided with each other. It released 3 solar masses. That's 3 times the whole mass of our sun from mass into energy out into space. And I think this is one of like the largest or the most energetic events that we've been able to record in cosmology.
Pretty big event.
Yeah. Well, yeah. Or not in priority, but in amount of energy that's exchanged at a single point that's verifiable. Right. And so that's, I think, what the type of thing that this type of observatory was looking for was something to collect these gravitational waves. So it's a really cool story. They've kind of figured that out. I think that was back in September that they made the observations. And then now in, what was it, mid-February, that's when they kind of announced it. Probably won't make a lot of changes for any daily use, but it will change a lot of the astronomical, well, I'd say like part of the study of astronomy going forward in the next 50 or 75 to 100 years, is because now we can make gravitational telescopes. We can make these tools that are able to observe gravity waves out in space. And this is just the first time that we've done it. This was an observation of one of the most strong signals or strong events that we'd be able to gravitationally pick up. And so now from here, over the next several generations of this technology, they're going to be able to refine it so much more that they're going to be able to pick up much more subtle gravitational waves. And once they're able to do this, or once they're able to, let's say, now that it's proven, put this type of technology out into space and then make that expanse really vast, we're going to be able to refine details of these gravitational waves to a much smaller resolution. And that's going to give scientists and cosmologists and these new gravitational wave astronomers more tools to look into the universe, and especially look into the early stages of the universe forming, which is going to be really exciting. I think this event that they observed was 1.5 billion light years away. They say it's not triangulated, so they don't know exactly where in space this event took place, but they say that it would be out somewhere past the Magellanic Cloud, if we were to kind of think about it in the sphere of the sky. That's in the southern hemisphere. Pretty cool stuff. The coolest thing. So it's kind of obtuse to sort of wrap your head around what it means, what are they observing, what is a gravitational wave, but this ripple from this event that happened 1.5 billion years ago sent a wave in gravity through space-time across the universe, and it had adjusted the width of the Milky Way galaxy by the width of your thumb.
Oh, wow.
Yeah.
That's
so in the room, there's, in any kind of human perceptible distance, there's no change. There's like an atom's width of change for us experiencing it here on Earth. That's why we didn't see any kind of crazy, thing happen. There's no kind of
Right.
observable event, even with something that's probably one of the strongest events observable for us, out in outer space. These collisions of black holes. Um, but yeah, that wave I think stretched and then shrunk the galaxy by the width of a thumb. So that's like 100 light years across. Excuse me, 100 light years. I think it's 100,000 light years across the Milky Way galaxy, and that kind of wiggled by an inch
Yeah.
with
So
this gravitational wave.
you're saying that it got a space in it that was the width of a thumb, and then it got closer together.
It's really strange. It warped space time, so there's no physical space that changed, but that it's complicated. Yeah, that the fabric between the atoms had flexed outward,
Right.
imperceivable to us as beings that don't have a capability of perceiving something like that, of the change in our space time. We're not able to really do that. We perceive, because since we're in it, we perceive time to be pretty constant. But if we were outside of that, we could see that the fabric of it, the size of it, stretched out an inch and then came back together. So if we think of the
Okay.
expanding universe, it's the expansion of space time that's traveling outward. So the physical distance between proton and proton in an atom is expanding outward, and the size of those atoms are expanding outward.
Okay.
It's like space time is expanding.
Right.
It's just sort of all expanding together. But in this situation, just this wave came through. Like we think of a wave on a beach, it rolled through, and like when we were in the waves in the ocean a few weeks ago, you'd kind of be in the wave, it would move through, but then it would go back to the status of the water before the
Right.
wave, right? So the wave similarly came through. It didn't displace anything or move anything permanently, but it just
Just
the
during that
wave,
time that was going through.
yeah, stretched it by some amount and then had it come back together. But that's the amount of distortion that was sent across from that gravitational wave. And gravitational waves, the reason that it's important to us is that it was the thing that was one of the last things to be identified, or how would that be? One of the last items in Einstein's theory of special relativity that was yet to be yet to be proven. So this
Mhm.
item of gravitational waves has really just been theoretical up until this point, because there had been no technology developed to make that an observable phenomena, these gravitational waves. And so
Right.
it's really this huge feat of engineering that we're even at a place where we can do that now.
Yeah. It's really pretty incredible. Is it? So now that they've officially, I guess, said that that's happened, they're going to be working on telescopes now, or newer telescopes that can detect that. Is that
Yeah,
what you're saying?
there's two locations right now, and these were all part of a scientific grant to look for a theoretical piece of science that no one believed even existed. Even Einstein, I think, kind of sort of tried to retract this idea during his life,
Okay.
that there was even the possibility of observing these gravitational waves. They were able to make this system to do that. It's a gravitational wave observatory. Really interesting stuff. I won't get into exactly how they do it, but it's a laser interferometer, and it uses like a period of an amount of time to bounce a laser beam back and forth. And if a gravitational wave goes through there and stretches space time out, then the wave of light takes longer than the speed of light to go all the way down to the end and then back. And so they're measuring that amount of time, that period, really, really accurately. And then when this happened, the wave came through, it stretched space time over that distance, and then the wave didn't come back at the right time. That means that there was a measurable gravitational wave that passed through that space time that stretched that tube of the observatory, and that's what they recorded. They did this in two locations, all part of the same, I don't know, observational. Um, well, there's two observatories. They both get recordings, and then they match that data together so that they can do noise cancellation to drop out any of the disturbances that be localized to the Earth. So if
Okay.
there's an earthquake in one, you could kind of measure that against whatever the other one would pick up, and you could cancel that signal out.
Okay.
Yeah, it's cool stuff. So now that it's been proven, now that this really experimental thing that cost billions of dollars to get set up for the first time has now been proven, it's going to be this huge expansion into the scientific community where they're going to be building out a lot more of these tools to do gravitational wave observations.
That's really cool.
It's going to be really exciting. Yeah, I'm really glad that it came through. We're going to see a huge expanse in the field of cosmology in our lifetime. Now that this is something that's out there that people, well, that astronomers will be able to do research on. It's going to be interesting to find out, I guess, what kind of new discoveries kind of come from this.
Yeah,
it'll take some time to vest, but it'll be really cool.
Yeah, it'll be really neat to see what new things we're figuring out.
Yeah, it'll be a lot of fun.
And so, what are the names of the observatories that proved this?
Yeah, so I think I mentioned that there are two observatories that were picking this up, and they were doing noise cancellation against each other to try and refine the signal, which is part of how the technology works that they're using. And so the installation is called LIGO. It's the Laser Interferometer Gravitational-Wave Observatory. It's an acronym, and there's two installation sites. Right now, they're both in America. I think they're going to expand soon out from that because there's going to be an advantage if there are, well, at least if there are more than two, because right now with two, they're not able to triangulate the position of a signal that they get. And so once they're able to triangulate things, that question that we had a few minutes ago when we were talking about where this event, this black hole collision took place in the universe, we'd be able to better pinpoint that answer if we have three of them, because we'll be able to triangulate that signal. So with the two of them, we're only able to tell right now that they're out in the Magellanic Cloud. So the two observatories that exist, one of them is in Washington State and one of them is in Arkansas right now. It's cool. Okay. I think the best place for them to be would be off the Earth entirely. So same as like the Hubble telescope. When we started doing optical observations of space above us, we used a telescope here on Earth, but really ultimately the best, highest resolution way that we can make observations of the universe was by putting that telescope outside the gravity well of the Earth and putting it out into space where there wouldn't be any disturbance from light pollution or atmosphere or vibration. And they could put this telescope up, make it perfectly still, and have it take these really long exposures or long periods of light collecting to get these images or to get this resolution of data so that they can look out so deeply into space. Really cool how they're able to do that with optical telescopes. I think in our lifetime, over the next 30, 40 years, if this seems like a promising field of science, we're going to see that expand out into laser interferometer gravitational wave observatories that are put out into space as like long satellites, or satellites that communicate to each other and send a pulse back and forth or send a laser back and forth to each other, and then try and pick up that same period of time as the technology and algorithms for this get a lot better. It'd be really cool.
Oh, it'd be really cool.
Yeah. Yeah, it would be really neat. So I think right now, since they have proven that there are gravitational waves, there is now funding made available for a third LIGO installment to, I think, be put into somewhere in the US. Probably take another 10 years for that installation to go online, I'd bet. We might see others like this come up from other educational institutions around the world. Like we might see something from CERN, or we might see something from, just from some other installation that would want to build something like this now that it's a provable, scientifically researchable field of cosmology. Be really cool. It's going to be one of the most exciting things that happens for this next century of scientific discovery. I think this is probably one of the groundbreaking things that'll be part of learning about gravity, learning about that part of early universal history. Be interesting.
Yeah, it'll be really interesting.
Yeah. Well, I'm glad we got to talk about it a little bit. And I want to say, on behalf of Marina Hansen, thank you very much, everyone, for listening to this episode of the Night Sky Podcast.